Welcome to the second lecture on the course 3G and 4G wireless communications. As we had seen in the previous lecture, we just started to describe the wireless communication environment. We started with the idea that in a wireless communication system, there is typically a base station which is mounted at a height, there is a mobile station, and the electromagnetic wave or the signal propagates from the base station to the mobile station via a direct path, and there are several scattered paths. This is the main difference or the essential difference between a wireless communication and a wired communication system, because in a wired communication system there is only a single path of propagation between the transmitter and receiver. Hence, the wireless communication environment, as we saw in the last lecture, is a multipath propagation environment, which means depending on the lengths and depending on the distances and depending on the attenuation of each path, the electromagnetic waves that are arriving from the different paths either add constructively or destructively at the wireless communication receiver. And we started by trying to characterize or trying to model or develop a mathematical model for this wireless communication system as a linear time invariant system, all right. And we said that the wireless communication system can be represented, or each path of the system can be represented by an attenuation A I belonging to the ith path and a delay tau I belonging to the ith path. So, if there are L minus or if there are L paths indexed 0, 1 up to L minus 1, we can represent it as a combination of follows. Each path can be represented as an LTI system with attenuation A I, and the delay tau I can be represented as delta of tau minus tau I. So, corresponding to the 0th path, I have the impulse response A 0 delta t minus tau 0. Corresponding to the first path, I have the impulse response A 1 delta t minus tau 1, so on and so forth up till A L minus 1 delta t minus tau L minus 1. And we also said that the complex baseband, using complex baseband passband notation, the wireless communication signal can be represented as real part of SBT times e power j 2 pi f c of t, where SB of t is the complex baseband signal and f c is the carrier frequency. And we saw several examples of possible carrier frequencies, and we started to derive the received signal at the mobile station after it passes through the channel. We said that passing through the first path, or the response or the received signal at the mobile station corresponding to the first path, is essentially the transmitted signal SB of t minus SB of t attenuated by A naught and delayed by tau naught. The received signal corresponding to path 1 is real part of A 1 SB t minus tau 1 e power j 2 pi f c t minus tau 1, which is essentially the transmitted signal attenuated by A 1 and delayed by tau 1, and so on and so forth until the signal corresponding to the L minus 1th path is essentially real part of A L minus 1, A L minus 1 is the attenuation corresponding to the L minus 1th path, S B t minus tau L minus 1, where tau L minus 1 is the delay corresponding to L minus 1th path, and e power j 2 pi f c t minus tau of L minus 1. Hence, the net signal, that is the net wireless signal, let me write it as the net signal, can be represented as the sum of all the signals arriving from the multipath components, or the sum of essentially all the signal copies arriving through the different paths, and that is simply y of t, which is real part of the sum of all the above components, and I can represent that compactly using the sum notation as sigma I equals 0 to L minus 1 A I S B t minus tau I e to the power of j 2 pi f c t minus tau I. That is, the received signal at the mobile station or the mobile phone can be represented as a combination of all the signals corresponding to each path, and that is simply represented succinctly as real part of summation I equals 0 L minus 1, that is the L paths. AI is the attenuation corresponding to the ith path, SB t minus tau I is the delay corresponding to the ith path, and e power j 2 pi f c t minus tau I, where this corresponds to the delay of the carrier. All right. So, thus we can derive the received signal corresponding to the signal that is received at the mobile station. Now, we have derived the received signal. Let me write that again for your convenience. This is the real part of sum I equals 0 to L minus 1 A I S B t minus tau I e power minus j 2 pi f c t minus tau I. Let me perform some manipulations on this expression, just a simple manipulation where I will take out the common factor e power j 2 pi f c t. I am sorry, this is e power j 2 pi f c t minus tau I, not minus, right. And this can be essentially be written as real part of I equals 0 to L minus 1 A I S B t minus tau I e power minus j 2 pi f c tau I, and the factor e power j 2 pi f c of t is common to all the terms, which is the carrier term. So, I am separating it out from the rest of the terms. Now, if you glance at the term in the bracket, this is some complex signal . This is some complex, the term in the inner brackets is a complex signal that is multiplied by e power j 2 pi f c t, which is the carrier term. And now, we know from the complex baseband passband representation that this is essentially the complex baseband received signal. For instance, let me go back a couple of slides. We said if you have a signal S t, which can be written as real part of S b t e power j 2 pi f c of t, then the complex signal S b t corresponds to the complex baseband signal. Similarly, here the signal, the complex signal in the brackets corresponds to the complex baseband received signal. All right. So, let me write this down explicitly, because this is going to be important for us. The complex baseband Rx. Remember, we introduced this notation Rx yesterday to denote the receiver. So, the complex baseband received signal is simply y b of t. Let me use the notation y b of t equals I equals 0 to L minus 1 AI SB t minus tau I e power minus j 2 pi f c tau I. All right. Let me box this because this is an important result which we are going to use. All right. So, the complex baseband received signal at the mobile station is y b of t, which is summation I equals 0 a I s b t minus tau I e power minus j 2 pi f c tau I. Now, first observe that the summation still has L components that correspond to the L terms that correspond to the L received multipath signal components. There is the attenuation factor A I, the delay factor tau I corresponding to the baseband signal, and also there is a complex phase factor e power minus j 2 pi f c tau I. This is a complex phase factor. Observe that this complex phase factor is arising out of the delay tau I. That is what we said. The different signals that are received at the mobile station by virtue of having traveled different distances add up with different phases at the receiver. This factor e power minus j 2 pi f c of tau I is essentially testimony to that fact that the delay is resulting in a phase of the path of the signal received at on the ith path at the mobile station. All right. So, let me describe this in a little bit more detail. Let me write this here again, that is the y b t, that is the received complex baseband signal can be simply given as I equals 0 a I s b t minus tau I e power minus j 2 pi f c tau I. A I is the attenuation, tau I is the delay of the ith path. And now, let me make a simplifying assumption which I will call the narrowband assumption and which is popularly known as the narrowband signal assumption. Let me describe what that means and give you an example. The narrowband assumption is follows. Let f m be the maximum frequency component of S b of t, that is f m is the maximum frequency component of the transmitted baseband signal S b of t. Let me draw a picture to tell you how that looks like. If the spectrum in the baseband looks as follows, that is from minus f m to f m, then this maximum frequency component present in the complex baseband signal is what we are denoting by f m, this quantity f m. All right. Now, if for instance, for a GSM signal the total bandwidth, that is 2 f m, is 200 kilohertz, which means f m is 100 kilohertz. All right. For instance, example GSM f m is 100 kilohertz. All right. Now, if f m less than 1 by tau I for all, this signal is a narrow band signal, right. This is the narrow band condition. If f m, this is the narrow band condition, that is if the maximum frequency in the baseband signal is less than 1 over tau I for all I, that is it's less than 1 over the delay of all the paths 0, 1, 2 up to L minus 1, then I call the signal narrow band. Now, typically tau I is approximately of the order of 1 microsecond. Right. So, tau is typically of the order of 1 microsecond. We will see the reason for this in the future lectures, but right now I urge you to accept this typical value of tau I. So, 1 over tau I is 1 over 1 microsecond, which corresponds to 1 megahertz. All right. Now, you can see for a GSM signal the FM is 100 kilohertz, which is much smaller than 1 over tau I, which is 1 megahertz. So, this is a narrow band signal, or for instance GSM is essentially is a narrow band right. What we mean is the GSM signal, transmitted GSM signal is a narrow band signal. There are many cases where this narrow band assumption is not valid. For instance, the very obvious case is CDMA, because by definition CDMA is a spread spectrum system, hence it is a wide band signal. So, such a generalization or such a simplification is not possible in the case of CDMA, or this assumption does not hold in the case of CDMA, it holds in the case of some signals. So, let us start with a narrow band signal to simplify the analysis, then we will look at how to handle a wide band signal in the future lectures. All right. So, now coming back to my baseband system model, which is YB of t is AI SB of t minus tau I e power minus j 2 pi FC of tau I. In case of a narrow band signal, for a narrow band signal, a simplifying assumption that can be made is SB of t minus tau I is approximately equal to SB of t. All right, what does this mean? This means that the baseband signal for different delays tau I is approximately equal to SB of t, that is the delay is insignificant, that the delay does not cause significant distortion in the received signal, because its maximum frequency component FM is limited. All right. Using this simplifying narrow band assumption, now if we go back to one slide, I have YBT equals the baseband signal is I equals 0 to L minus 1 AI SBT minus tau I e power minus j 2 pi FC tau I. Now, all the SB t minus tau i's are approximately equal to SBT, which means this SBT comes out of this expression, and I can write a simplified expression for the narrow band for a narrow band received signal as follows, that is YB of t equals SB of t into sigma I equals 0 to L minus 1 e power minus j 2 pi FC tau I, and this is a very important expression. Let me recap what we have done. We have modeled the wireless channel as a channel with multiple propagation paths consisting of attenuations and delays. We modeled the wireless transmitted signal as a complex baseband signal modulating a carrier. Now, what this result says here is that if the baseband signal is a narrowband signal such as a GSM, what I receive at the output is essentially the transmitted signal SB of t. Look at this, this is the transmitted baseband signal. This is the transmitted baseband signal multiplied by a phase factor, that is the input SBT is multiplied or scaled by a complex phase factor, and that is the complex received signal. Alright. So, this is a complex, not just a phase factor, but a complex factor. Also a complex coefficient. Alright. So, the output YBT is SB of t, the input, times a complex coefficient. Alright. And this has a name, this is known as the complex fading coefficient. We will see the reason for this soon. Now, one thing you can observe is right away, depending on the tau i's, the different tau i's, and forgive me, there also has to be an AI over here. Depending on the different AI's, different tau i's, these different complex numbers can add up to either produce constructive interference or destructive interference. For instance, let me give you an example. Let me take an example over here. Let me consider a case of L equals 2 paths, and let me consider the attenuation of the first path is 1, that is there is no attenuation, the magnitude of the input is the magnitude of the output, and the delay is also 0, that is tau 0 equals 0. Let me look at another example. Let me consider another path where A1 is also equal to 1, that is there is no attenuation or amplification for the first path. However, the delay of the first path is 1 over 2 Fc. Alright. So, what I am saying is the delay. So, A0, there are two paths in this system, there are two paths in this wireless channel. One is the direct path, which has an attenuation of 1 and delay of 0, and another path which has an attenuation, which also has an attenuation of 1, but a delay of 1 over 2 Fc. Now, if I look at the coefficient, let me give the complex coefficient a name. The complex coefficient, which I will denote by H, equals sigma I equals 0 to L minus 1 A I e power minus j 2 pi F c tau I. Now, this has obviously this has L equals 2. So, this goes from I equals 0 to 1 A I e power minus j 2 pi F c tau I. Now, for the first path, this is A0, which is 1 times e power minus j 2 pi F c tau 0, tau 0 is 0. So, e power minus j 2 pi F c tau 0 is e power 0, which is 1. So, this is 1 plus A1 times e power minus j 2 pi F c tau 1, A1 is 1 into e power minus j 2 pi F c times tau 1, which is 1 over 2 F c. So, this is e power minus j pi. Now, you can see this value is 1 plus e power minus j pi is minus 1. So, this is 1 plus minus 1, which is 0. For this example, what does this mean? It means that if I have two paths having same attenuation factors, that is 1 and 1, however, one has a relative delay of 1 over 2 F c corresponding to the other, then the complex coefficient is 0, which means the received signal, for the above example equals S b of t times the coefficient, which is 0, equals 0, alright, which means there is no received signal because the paths are adding up destructively. That is the problem here. So, even though you are transmitting a signal, because both the paths, by virtue of one path being delayed compared to the other path, they are cancelling each other, and as a result you are not getting any signal at the receiver. Now, as alternate to that, consider another scenario where A0, again I am considering L equals 2 paths, A0 equals 1, A1 equals 1. However, the delays now are tau 0 equals 0 and tau 1 equals 1 over Fc. You can easily show in this case that the coefficient is H equals 1 plus 1 equals 2, and hence the received signal is Yb of t equals Sb of t into 2 equals 2 Sb of t. In this case, the signals from both the parts are adding up constructively in phase to give you Sb of t plus Sb of t, that is one copy from the direct path, another copy from the scattered path, adding up coherently to give you 2 Sb of t. So, the signal amplitude is twice, which means the received power is 4 times the transmitted power, alright. So, amplitude is twice, the received signal power is 4 times the transmitted power. Let me just write this down clearly as Sb of t, alright. In this case, Yb of t is 2 Sb of t. So, what have we observed so far? What we have observed essentially is the fact that if one of the paths is delayed 1 over 2 Fc compared to the other path, then the total received signal is 0 because they cancel out each other. If one of the paths is delayed 1 over Fc relative to the other, then they add up constructively, hence the total received signal is twice Sb of t, that is twice in amplitude, hence it is 4 times in power. And for all values of delay between 1 over 2 Fc and Fc, the signal amplitude varies between 0 Sbt, that is 0, and twice Sbt. So, what I wish to bring to your attention here is the fact that because of the random nature of this multipath components, what you receive might be 0, that is you are not receiving any signal, or what you receive might be proportional, might be twice, or even depending on the number of components, thrice, and so on. So, you receive a range of signal powers at the receiver, alright. You receive a range of signal powers at the receiver depending on the random nature of the multipath components in the channel. So, at the receiver, it looks as if the signal is going through a set of various strengths. For instance, in one case you might receive a signal of very poor power, 0 power. In other case you might receive a signal of very high power. So, if you plot the signal quality versus time, it will look as some curve where the signal power, for instance this is the power and this is the time. So, the signal power is varying in time. For instance, here it is very low, here it is probably high, and so on, and this variation in the signal power is known as fading. The signal power waxes and wanes, and this variation is essentially what is termed as fading, and it is a very important characteristic of the wireless propagation environment arising due to the multipath propagation environment. Remember, this does not arise in a wireline propagation environment, because in a wireline propagation environment there is a single path between the transmitter and receiver, which means there is no constructive or destructive interference at the receiver, because there is only a single path, and the signal that is transmitted is the signal that is essentially received. Alright. So, if I analytically model a wire line communication system, let me just compare analytical models of wire line and wireless communication system. In a wireless communication system, we said that the received signal y b of t equals h times s b of t, where h is the complex coefficient, and now we can also give it a new name. We can call it the complex fading coefficient. This is the complex fading coefficient, fading because this is what results in the fading nature of the received signal at the receiver. And for a traditional wired system or wired or wire line system, these are typically known as wire line systems, the received signal y b of t is simply s b of t. The received signal y b of t is simply s b of t because there is only a single path and there is no multipath interference. So, what you transmit is what you receive. Of course, in both cases there will be noise at the receiver, we will see the effect of this later, but the effect of the signal, I mean in terms of the signal, if you look purely in terms of the signal, in a wireless system what you receive is h times s b t, where h is the complex flat fading coefficient, and in a wire line system y b t or the received signal is simply s b t, that is the transmitted signal. And this is a very important difference between wireless and wire line communication systems. What we are going to do next is we are going to compare wireless and wireline systems, but before that we will try to better understand the properties of this complex fading coefficient as h. What we will try to do is we will try to statistically analyze this h and draw some conclusions about its behavior or conclusions about the randomness of this h. I mean what kind of behavior does this complex fading coefficient h exhibit. So, I go to the next section, and this section is essentially titled as statistics of the fading this section is titled as statistics of the fading coefficient. Let me remind you, the fading coefficient is h, which is equal to I equals 0 to L minus 1 a I e power minus j 2 pi f c tau I. This is the fading coefficient. This can also be represented as a complex number x plus j y, all right, also represented in magnitude and phase form as a e power j pi. What I am saying is as follows: this is a complex number h, which is given by this expression summation I equals 0 to L minus 1 a I e power minus j 2 pi f c of tau I. This can be represented using the real part and imaginary part format of x plus j y, where x is the real part of this quantity, y is the imaginary part, and also the magnitude and phase notation, where a is the magnitude of this quantity and phi is the phase of this quantity. All right. And now, what does this essentially look like? Let me expand this a little bit further. This is essentially I equals 0 or to L minus 1 a I cosine 2 pi f c tau I minus b I cosine 2 pi f c tau I. I am expanding the minus j b I sine 2 pi f c tau I. I am expanding each complex factor here as a I e power minus as I am expanding the e power minus j 2 pi f c tau I as cosine 2 pi f c tau I minus sine 2 pi f c tau I. Sorry, this b I should rather be an a I. All right, and now the real part of this is simply x equals a I cosine 2 pi f c tau I and y equals b I minus b I sine 2 pi f c tau I. Alright, so I have expanded the complex fading coefficient as a sum of a real part and an imaginary part. X, which is the real part, is simply summation, or it is rather summation a I cosine 2 pi f c of t I, and y is summation minus b I sine 2 pi f c of t I. So, I can express the real part x as sigma I equals 0 L minus 1 a I cosine 2 pi f c tau I, and the imaginary part y of the complex fading coefficient as minus sigma I equals 0 L minus 1 a I sine 2 pi f c tau I. Now, in general it is very difficult to explicitly estimate or explicitly arrive at values of each of the AIs and each of the tau I's in a real time wireless communication system, or explicitly characterize each of these. So, what the approach that is followed is to instead characterize each of them separately, try to characterize the properties of the complex fading coefficient as a whole, that is to try to characterize the behavior of this complex fading coefficient, and for that process, or to characterize the behavior of this fading coefficient, we will take the help of the theory of random processes and statistics and probability. So, let me start by refreshing your knowledge about Gaussian random processes. So, let me start with a brief review of Gaussian random process and Gaussian random variables. A Gaussian random variable x, which is x, is a Gaussian random variable with mean mu and variance sigma square. That is, if x is a Gaussian random variable with mean mu and variance sigma square, it has a probability density function that is given as f x of x equals 1 over square root of 2 pi sigma square e power minus x minus mu whole square divided by 2 sigma square. That is the probability density distribution density function of a Gaussian random variable f x of x is given as 1 over square root of 2 pi sigma square minus x minus mu whole square divided by 2 sigma square. All right, and this has a shape that looks as follows. Let me draw the approximate shape. This is the PDF of a Gaussian random variable centered at the mean of this random variable, which is mu, and this has a spread which is essentially proportional. This is proportional to sigma. This is proportional to sigma. All right, the variance is sigma square, the spread is proportional, or the deviation is proportional to sigma. All right. So, and there is a very specific kind of random variable, Gaussian random variable, which is the standard normal or the standard Gaussian random variable. It is simply the Gaussian random variable with mean 0 and variance 1, and that has a PDF obviously, which is 1 over 2 pi, sigma square is 1. So, 1 over square root of 2 pi sigma square is simply 1 over square root of 2 pi, e power minus mu is 0. So, x minus mu is x and x minus mu square is x square divided by 2 sigma square is 1. So, simply divided by 2. This is the PDF of the standard normal or the probability density function of the standard Gaussian we will use Gaussian random variables and the properties of Gaussian random variables extensively in the analysis that follows and extensively throughout this course on wireless communications. So, I would urge all students, all viewers to kindly review your knowledge of probability, random processes, probability distribution functions. As we have already seen, this information is available in the NPTEL course on communication engineering. Now, going back to our problem of the complex fading coefficient, where h is x plus j y, that this is h is the complex fading coefficient. I am going back to our analysis of the complex fading coefficient, which is x plus j y, and we have seen that each x and each j y is a sum of a large number of random components, that is x and y are both sum of a large number of random components. Why are these components random? Because remember, each of these components is arising from the multipath environment. These correspond to every path, and these essentially correspond to the distance between the base station and the mobile station, and also how the scatterers are placed. What is the distance of the trees, what is the distance of the buildings, what is the distance of the cars, and so on. And each of them is a random quantity depending on the scenario, and hence the real part x, which is a summation a I cos 2 pi f c tau I, and the imaginary part, which is minus sum a I sin 2 pi f c tau I, are both random numbers depending on the which depend on the random quantities a I's, which are the attenuations, and the delays, which are tau I. All right. So, these are the each x and y are the sum of a large number of random components, and from standard results in probability theory, we can assume when a random quantity is derived as the sum of a large number of other random quantities, it can be assumed to be Gaussian in nature. So, we will assume x and y to be Gaussian in nature. That is, x and y are Gaussian random variables because they are derived as the sum of a large number of random components. All right, and for more details, you can refer to an advanced property known as central limit theorem, as the central limit theorem, which gives more information about why a large number of random quantities, when they add up, result in a Gaussian random variable. For the purpose of our analysis, we can assume safely that this x and y exhibit Gaussian nature. So, let us start with a basic assumption, that is h equals x plus j y. I will assume x to be Gaussian distributed. I am using this notation, a standard Gaussian notation, which is x is n 0 half, that is x is a Gaussian random variable of mean 0, variance half, y is another Gaussian random variable of mean 0 and variance half, and further I will assume that x and y are independent. Random variables. Alright, x and y are independent random variables, which means the probability distribution, the joint distribution of x y is given as the product of the distributions of x and y, and we know the distribution of x because x is a Gaussian random variable of mean 0, variance half. So, the distribution of x is simply f x of x equals 1 by square root of 2 pi sigma square, but sigma square is half, times e power minus x minus mu square, mu is 0. So, it is simply x square divided by 2 sigma square is half. So, it is 2 into half, which is 1. So, I can write the distribution of x simply as 1 over square root of pi e power minus x square. Similarly, the distribution of y, which is the real part or which is the imaginary part of the fading coefficient, that is also assumed to be another normal random variable of mean 0 and variance half. So, its distribution is 1 over square root of pi e power minus y square. All right. Now, as we said or as we assumed that the x and y are independent random variables, hence the joint distribution x comma y or f x y of x y is simply given as 1 over root pi e power minus x square times 1 over square root of pi e power minus y square. This is simply 1 over pi e power minus x square plus y square. So, we have successfully derived the joint distribution of this random variable x of the components of the flat fading coefficient h, which are x and y. All right. Now, what I want to do is convert this distribution or modify this distribution in terms of x and y into a and phi, where a is the magnitude of the fading coefficient and phi is the phase of the fading coefficient. Remember, we wrote h as x plus j y, which can also be expressed as a e power j phi, where a is the magnitude and phi is the phase of the complex fading coefficient, or in other words, x equals a cosine phi, y equals a sin phi. So, x, that is the real part, is a times cosine of phi, y, the imaginary part, is a times sin of phi. We already have the joint distribution of x and y. I want to now derive the joint distribution of a and phi, and that will give us a better idea, because remember, a is the magnitude of this fading coefficient. So, it gives me an idea of the power or the gain between the transmitter and the receiver, and this is an important aspect of any wireless communication system. That is, a square is the gain of the communication system. Hence, I want to characterize this in terms of a and phi, so I can study the behavior of this random variable a. All right. For that purpose, I will use the standard result, that is, if I have to convert a distribution, that is, if I want to derive the distribution in terms of random, in terms of parameters a and phi, given the distribution in terms of x and y, I can convert that distribution as follows. First, let me derive the expression for x square plus y square. X square plus y square equals a square cos square phi plus a square sin square phi, which is simply a square cosine square phi plus sin square phi, which is equal to a square. Hence, remember the joint distribution in terms of x and y is given as 1 over pi e power minus x square plus y square, that is 1 over pi e power minus x square plus y square. Hence, the joint distribution in terms of a comma phi is 1 over pi e power minus x square plus y square. However, we have seen that x square plus y square is a square. So, this is 1 over pi e power minus a square, and there is one more term which is known as the determinant of the Jacobian matrix of x y. This is a scaling term. Let me define what the Jacobian matrix is. The Jacobian of x y is essentially dou the partial derivative of x with respect to a, the partial derivative of y with respect to a, the partial derivative of x with respect to phi, and the partial derivative of y with respect to phi. Alright, this is the Jacobian, which is essentially the partial derivative, which is a 2 cross 2 matrix. In this case, the first entry is the partial derivative of x with respect to a, the second entry is partial derivative of y with respect to a, the other entries are partial derivative of x with respect to phi and the partial derivative of y with respect to phi, and this is simply given as, remember, x equals a cosine phi. So, the partial derivative of x with respect to a is simply derivative of a cosine phi with respect to a, which is cosine phi. The partial derivative of y with respect to a is similarly sin phi. The partial derivative of x with respect to phi is the derivative of a cosine phi with respect to phi, which is minus of a sin phi, and the derivative of a sin phi with respect to phi is simply a cosine phi. Alright, this is the Jacobian matrix. We now want to compute the determinant of this Jacobian matrix, that is the determinant of this Jacobian matrix. Let me go back to the previous slide. If you look at the Jacobian matrix, one can clearly see the determinant of this Jacobian matrix is cosine phi times a cosine phi, that is a cosine square phi, minus of a sin phi into sin phi, that is minus a sin square phi. So, let me write this down. The determinant of this Jacobian matrix is a cosine phi times cosine phi minus a sin phi times sin phi, which is a cosine square phi plus a sin square phi, which is essentially a. So, now we have completed derived the Jacobian, and now I want to substitute the Jacobian into this expression here, which is the expression for the joint distribution in terms of a phi, that is 1 over pi e power minus a square times the determinant of the Jacobian, and hence the joint distribution is simply f of a phi equals 1 over pi e power minus a square times the determinant of the Jacobian, which is simply a, and hence the distribution is simply a over pi e power minus a square. With this, I would like to conclude this second lecture on 3G and 4G wireless communications. We will start with this joint distribution of the channel fading coefficient in terms of a and phi, and move on to and continue this discussion further in the next lecture. Thank you.